So, numerical optimization. This talk will be based on some slide material that I got from colleagues in Heidelberg long ago, some of the figures, and it will have 3 parts. The first 2 will be quite basic, and my idea is really to share a very high level perspective on optimization with you, with some clean mathematical definitions, of course. First, basic definitions, then some classes of optimization problems that I think are important, so that we all know about that. And afterwards, a class of algorithms that we call Newton type optimization, which are useful for solving one particular class of optimization problems, namely nonlinear programs. So, basic definitions and concepts. What is optimization? It's the search, so to say, for the best solution. And in mathematical terms, it's either minimization or maximization of an objective function that we call f, and subject to some constraints. And I should say that maximizing a function is the same as minimizing the negative of this function. So you don't have to change anything apart from the sign when we talk about minimization or maximization algorithms. I will mostly talk about minimizing, Joschka sometimes about maximizing, but we are all okay with that, I think. So very often we have constraints, and for example, the variable should be positive, or it should be on a circle like this. X1 square plus x2 square should be a constant. And generally we formulate an optimization problem so that it has an objective function that we want to minimize, f of x, subject to some constraints which are equalities, g, possibly many, so this is a vector valued function, and some inequalities, h, also a vector valued function. Each component should be positive. So that's the statement of an optimization problem. And to give you an example, I actually still use my little example with a ball. Okay, and it's not a ball, it's this bottle hanging on a spring. So this is actually this, right? But now we don't want to simulate this as a dynamic system, but we just want to use optimization to find the position at rest. And here we use some physics background, which would say that a system always looks for the position where its potential energy is at rest. And interestingly, if you would have a ball hanging on a spring like this thing, and then you add some constraints, this isn't a ball, that makes things a bit more complicated, right? But if you add constraints, for example, here a constraint, it would find a different rest position, obviously. And if you have oblique constraints, things get more interesting still, right? So the question is, where does the ball come to rest in this context? Does it actually touch one of the left, or even does it touch the corner, or doesn't it touch any of these constraints? And that is something that an optimization algorithm could find out. So to find the position at rest, one could just minimize the potential energy, like here the spring constant and gravity part, and then subject to 2 constraints which describe these 2 inequalities, right? So think of mechanical system. And I think it's good to have this mechanical system analogy, because also the constraints, they somehow exert some forces to the ball. And these forces we can actually interpret, or actually we will later call them Lagrange multipliers. Okay, so that's just something to imagine. And I think it's important to clarify the language. There is what we call the feasible set of an optimization problem. The feasible set is the collection of all points that satisfy all constraints, not one constraint, but all together. And so if you think of each single constraint describing some set, then the feasible set is the intersection of all the feasible sets of the single constraints, right? So all of them should be satisfied. If you have, for example, the constraint h1, which is equal to x2, that should be bigger than 0, then this describes this gray region at the top. The other constraint here might say that actually the x1 square plus x2 square should be smaller than 1, right? Expressed here with this inequality. That is actually everything that's inside the circle, and then the intersection of the 2 is this feasible set, the dark gray area. And so in mathematical terms, the feasible set is defined at the bottom, all points in the space that satisfy all constraints, right? Geometrically, imagine it as the intersection of lots of single constraints. Oh yeah. Then we have the notion of local and global minima. We are all familiar with that, but let's repeat what it is. A global minimum is something that is so that all feasible points have either a bigger or an equal objective value than our local, our global maximizer. That's the formula here at the bottom. And the local minimum is, or local minimizer, as we should call it more exactly, like the point that takes the value is the minimizer, right? And the value that it takes is the minimum, right? That would be the really clean language here. But very often we don't use very clean language. But here at the bottom we do. So we have a local minimizer if there is there is a neighborhood around that point where this point is the only and the best feasible point, right? So there's no better feasible point in this neighborhood. That's what a local minimizer is, and obviously there can be different local minima of different values even, but only one global minimum, even though there could be several global minimizers, right? So there could be many points that take it, but there's only one best value, obviously. We will also use derivatives quite a lot, and I think it's clean to talk once about what we have in mind here. First and second order derivatives are really the prime objects in optimization, and first order derivatives are just called the gradient. And please think of a scalar function f, yeah, and the gradient is a standing vector. That's why we have this transpose sign here of all the partial derivatives. That's what a gradient is for us, a standing vector, yeah. And the second order derivatives of a scalar function are this nabla squared of f. And that's a matrix, it's a symmetric matrix, and we call it the Hessian matrix. We will sometimes refer to Hessian matrices here. So now we have unconstrained optimality conditions, which we are probably familiar with in Rn. So that's slightly different from this picture and from school mathematics, n-dimensional. And so if you have an f that's twice differentiable, and you want to test if a point is locally optimal, then there's a necessary condition that says the gradient should be 0. We call this also stationary points. So gradient 0 could be a maximum, could be a minimum, could be anything like a intermediate, what we call a saddle point. But there's also a sufficient condition. And that is if the gradient is 0 and the second order derivative, this Hessian matrix, is a positive definite matrix, that means all its eigenvalues are positive, then it is a local minimum. Yeah. Please note, a symmetric matrix always has real eigenvalues only. So these eigenvalues are really real numbers, but they could be negative, 0, or positive. And if all are positive, then we have a positive definite matrix. And this is then a sufficient condition for local optimality. Imagine this as positive curvature. And I think this is here illustrated in these 3 plots. You can have different stationary points, so flat points, but left is what we really like, minimizers, right? Positive definite means positive curvature. But then B is a maximum, right? So then we have a negative definite matrix. It's also sometimes useful to know, right? So all eigenvalues negative, looks like a hill, like Schauinsland or something, right? A nice mountain here. And then you have these saddle points where the matrix, the Hessian matrix, is indefinite. That means you have some positive and some negative curvature directions. And these saddle points obviously aren't minimizers nor maximizers. They are just saddle points. That's why they are called like that. They look a bit like a saddle. That's why they are called saddle points. So let's look at this ball on a spring, but just the situation without any constraint. There we have this unconstrained minimization, just the objective function. You can visualize an objective function by so-called contour lines. I like these contour lines. They are actually, yeah, usually centered around the minimum, right? We can compute the gradient vectors. They here point away from this minimum. Obviously, they get bigger and bigger the further you go away. And then the unconstrained minimum, you could, in this case, just compute the gradient, set this to 0, and then you can easily do the math and you get the solution, which is in this case 0 and minus m half, yeah, just for this problem that we have here at the top. This would be easy, right? But I should say that sometimes there are many local minima, right? Or many local minimizers. Sometimes you have these molecule folding problems where you also want to find the minimum potential energy of a molecule, like protein folding, and there seems to be a lot of local minimizers. And I should say that global optimization is a very hard issue, so you usually don't try it. I mean, not in the context of big problems like we like to treat them. And so most algorithms that we ever talk here in this lecture, be it in machine learning or be it in nonlinear optimization, they just find the next, so to say, local minimum, some local minimum, and we are happy with that. Yeah. And the reason is that it works well in practice. That's one thing, right? Local minimizers are very often good enough, let's say. And also there is one reason. So some problems, and surprisingly many, are convex or close to convex. And that is the favorable special case, which I want to define cleanly here. So what is a convex function? A convex function is a function where all connecting lines between points on the graph are above the graph. That's what we have to imagine here on the left. If there's only one line that goes, so to say, 1 secant that goes under the graph, then the function isn't convex. Yeah? Mathematically, you can express it like this. So for all x and y and all t on the interval 0, 1, the function evaluated on the middle point must be below the linear interpolation between the two extreme points. So that's the definition of a convex function. And a convex function is nice. You can already imagine it has probably only one local minimum, and that's actually the case. Yeah? Convex feasible sets are the other notion that we need to know to define what is a convex optimization problem. And the convex set is a set when you take 2 points and you connect them with a line, the whole line must be in the set. That's the definition of a convex set. And so mathematically, you could say omega is convex if for all points in omega, x and y, and all t in 0, 1, the point on the convex combination of x and y is also in omega. So these are the notions that we need to define what is a convex optimization problem. And if you have a convex objective function and a convex feasible set, then we say the optimization problem is convex. And it turns out that for a convex problem, every local minimum is also a global minimum. All right, so there is basically only one local and global minimum. And that means for convex problem, it's really sufficient to find local minima. So it's enough to just search for a local minimum. And this sounds maybe restrictive, and it is. And many problems are not convex, but some are, and we should be able to recognize them. And that's one of the aims of this lecture, that you get a feeling what interesting problems could be convex problems. So let's look at characteristics of optimization problems. So first question, when you have an optimization problem and I ask you, what is your problem about? Then I would ask, how many variables do you have? Yeah, maybe 10, 100, 10,000. Then, very important, what is your search space? Do you have continuous variables like real numbers, real vectors, or do you have discrete numbers maybe? Do you have a combinatorial problem? And then maybe, do you know something about your function? Do you think it's convex, or does it have lots of local minima or not so many? So this is something a bit more fuzzy, right? But you would be interested in knowing about these things. The second question could be about the properties of your objective. So do you maybe have a linear objective function, just a linear function, or could it be nonlinear, general nonlinear? Maybe it's quadratic. That's very often in MPC, for example. And then questions like smoothness. Is it continuous or differentiable? Maybe twice, 3 times differentiable, infinitely many times. And another important question, do you have constraints or don't you have constraints? Maybe you don't have. And if you have constraints, are there equalities? No? Are there many equalities? Maybe there are as many equalities as you have decision variables, and there's no degrees of freedom left, right? Or do you have inequalities? Lots. Do you have maybe just bounds like upper and lower limits? Do you have linear inequalities or even nonlinear? Or maybe dynamic equations like we have in optimal control problems? And also these constraints can be smooth or not. What you see here on the right is, for example, that's actually the objective function of, that's the largest eigenvalue of a matrix as a function of the matrix entries, a very non-convex and unfortunately also non-smooth function. It's like the spectral radius of some dynamic systems. So to summarize what we have just touched, Please keep in mind, optimization problems can be unconstrained or constrained. They can be convex or non-convex. They can be linear or non-linear, differentiable or non-smooth, continuous or mixed integer, finite or infinite dimensional. So the dimensionality of the search space could also be infinite dimensional. And I want to directly go into 6 classes just to get a bit of an idea of what is out there. It's a very personal selection. And I start, as you might guess, with linear programming, which was, as I said, somehow at the origin of the field of mathematical programming. And mathematically, it's just an optimization problem where your objective function is linear. So there's a fixed vector C multiplied with X. There's a matrix A, a vector B, and then you say all the X components should be positive. That's a kind of standard form for LPs. And with some slack variables, you can transform every LP into the standard form if you want. And one example would be logistics problems. I don't go into details, but you can bring things like if you want to ship quantities of one product from M locations to N destinations, then you could formulate these things as an LP. So from every location to every destination, there could be a path and maybe some cost of shipping the things from here to there. Amazon would have tons of such problems, I guess, with their warehouses. And then you want to somehow minimize the total cost by moving the things to the closer centers. But you might have some constraints. You want to have certain amounts of product at each destination, for example. I should say that this comes from military applications, or a lot of these things started in the logistics of the Second World War on the Allies side. So quadratic programming is a generalization of this whole thing. It's very simple in the sense that it's only adding one extra term here, this 1/2 x transpose times q times x. Yeah? Q is a symmetric matrix. If it's not symmetric, only the symmetric part survives this product with x on left and right. So you can think of it as a symmetric matrix. And if this matrix Q is positive definite or positive semi-definite, then actually we call it a convex QP. And that's much easier than a non-convex QP. One example, I should say that I have a personal connection to, because it was my introduction to the whole field of optimization, is Markowitz mean variance portfolio optimization. It's something Markowitz got a Nobel Prize for by formulating the risk-return problem of portfolio allocation as a QP and then solving that reliably. And that's done, let's say, on a daily basis, probably every microsecond on many banks' computers nowadays. So they solve lots of QPs to just compute risk-return curves. And I don't go into the details here, but I just wanted to say that when I was during my studies of physics, doing an internship at a business consultancy and sitting in an insurance company, they decided to put me on the quantitative side, and they called me the quant of the team and said I should deal with portfolio optimization. And then basically I was formulating problems, and I didn't know that they were QPs, so I solved them with some stupid search method, like the Excel search solver, which is a very slow algorithm. And it took ages to optimize something. And at the very end of my internship there, I got a dedicated QP solver for the same problem. And I realized, oh, that's 10,000 times faster for the same problem. And then I realized that there's something in optimization. Searching for a solution with a search method can be extremely slow, and solving it with a dedicated solver can be many orders of magnitude faster. So that's what drew me into the area of algorithmic optimization. And maybe I should also say for us, it's particularly important. Quadratic programming is at the core of linear model predictive control. So when you have a linear predictive controller running on some industrial system, as I said, it's running since 30, 40 years on many processes in the chemical industry. It's mostly based on QPs, quadratic programs. Yeah, so they just solve such problems for different data. You can go further, and then you're in this class of nonlinear programming, which is basically covering the previous two also. Here we just say the functions f, h, and g are some possibly nonlinear functions, but we can differentiate them. So we assume that they are differentiable, typically. Once, twice, hopefully even more. One example that I think is good to have in mind how these things can look like is this Rosenbrock function. It's actually an unconstrained nonlinear problem, but this is a beautiful nonlinear banana valley function. It has a minimizer here, and it's relatively difficult to find that by just searching, so to say, and also going downhill, you will very often be very slow. So it's a good test problem for basic algorithms. And I should say that nonlinear MPC, which is a very widely used technique for control of systems, nonlinear systems is based on the online solution of nonlinear programs. So that's also why this class is particularly important. And we will focus on this class in the second part of this lecture, in the third part. So last, maybe just to mention, there is a field of non-smooth optimization. When the objective function or the constraints are not differentiable. Yeah, so for example, the first or the second derivative might not always exist. And you might say, oh, this is a bit strange, right? Why would it happen? But it happens so easily as here, the absolute value of x. That's non-smooth, right? The maximum of several functions is non-smooth. This here is even jumpy, I think, this function. And I mean, there could be nastier non-smoothnesses than others. But one important thing maybe to note is, if you take a ReLU activation function, for example, in neural networks, yeah, that is a non-differentiable function. And still people optimize with derivatives on this non-differentiable function. And it seems to be useful. Yeah, it works. So surprisingly, I would say, derivative-based methods still play a role for lots of non-smooth optimization problems. And there is some dedicated non-smooth solvers, but they are typically very slow, like bundle methods and so on. But you can use some actually derivative-based and usually smoothness requiring methods and just apply them to non-smooth problems. With some tricks, you can very often get surprisingly good solutions. Stochastic gradient descent is one. Also penalty methods for mathematical programs with complementarity constraints is something I find also extremely powerful and surprisingly good at finding good local minima of non-smooth functions. Another class I want to draw your attention to is integer programming. Very often it's mixed integer programming. If you have a mix of integer variables and continuous variables as your decision space. And typically when people say mixed integer programming, they have in mind linear mixed integer programming, which is already complex enough, right? So here you have just a linear objective, linear constraints, but then the constraint that you want to be in a integer space. And a lot of problems can be formulated with very dedicated techniques, which I don't want to detail here. But for example, traveling salesman problems, lots of logistics problems, a lot of things can be brought into mixed integer programming. And I think if you're experienced in that field, you could say everything can be modeled with mixed integer programming. Huh? And with linear mixed integer programming. And the reason is that, I mean, basically also nonlinear functions you can approximate as piecewise smooth. You get lots of switching variables, but in theory you can approximate every problem somehow with a mixed integer program. It's good to be aware of that. Sometimes this helps, sometimes it's just useless. But there's, I mean, you should not be unaware of the fact that there is a huge field of integer optimizers out there, thousands of smart people developing extremely powerful algorithms such as the Gurobi solver, getting better every year and solving huge and larger problems again and again. So this is an extremely powerful and big sub-area of optimization. And the last class I wanted to draw your attention to is optimal control problems. That's what I'm most interested in. It's like a continuous dynamic system. And then you want to optimize with it. So please note that the decision space is typically infinite dimensional, right? What happened here? I touched the blackboard, okay. And also your constraints are infinite dimensional. Because this ODE is infinite dimensional. And after discretization, we usually transform that to finite dimensions, but originally it's infinite dimensional. Sorry for the disturbances. I don't know. I think it has to do with my walking. Okay, maybe don't touch anything. So to bring this point a bit closer to your attention, let's say in nonlinear MPC, what we want to solve is at the end a nonlinear program. And I want to briefly sketch already how that's done so that we get motivation for nonlinear programming. So here's a continuous time model predictive control problem, a nonlinear one with this nonlinear dynamics f, c that I said before, right? And the constraints, as I said, are infinite dimensional. So for every t, which is a continuously varying variable, you have this ODE. And then your decision variables are also infinite dimensional. All the state trajectory is a function in function space. A is a function in function space. And then we go to this with our direct method. Direct multiple shooting, for example. Direct means let's first discretize the control. Don't let it be infinite dimensional. We have our control now with finite piecewise constant steps, for example. We discretize the problem and only then we optimize. I think it's when I touch the screen. Okay. So now we can formulate after this discretization a discrete time NMPC problem. That looks like the thing here on the right. You are already familiar with this f of s and a, the dynamic function. That's now a lot of equality constraints. They constrain our state trajectory s. And they also constrain it together with the control trajectory a. So these variables together, they form a very large vector x, extremely large, both trajectories together, but it's finite dimensional now. And then we are basically at a nonlinear program. So let me focus what this nonlinear program is. So let's move it to the left and just summarize it as this. So we just say there is an objective function, just these objective terms here, and then lots of equality constraints in this big function, this big G of x. Yeah, so that contains all these things, yeah, stacked on top of each other for k going from 0 to n minus 1. And then we stack all the inequality constraints on top of each other. That's this function big H. Yeah, so these are huge functions, depending on lots of parameters, but finite dimensional, and that's an NLP. And that's why we want to solve NLPs, because for nonlinear system models, we have to solve NLPs. So before I do a break for discussion, I want to give a famous quote. So whenever you formulate and solve optimization problems, don't forget the, so to say, the big watershed that's in the field of optimization. And here I cite a famous convex optimizer, Rockefeller, who said the great watershed in optimization isn't between linearity and nonlinearity, but between convexity and non-convexity, right? So there's lots of convex problems out there that might be nonlinear, but they are still convex. And they are really useful to know about, like QP, for example, right? And what we know is that for convex optimization problems, we can very efficiently find the global minimizer. That's extremely useful and extremely powerful, right? And let's say a side notion is that for non-convex but smooth problems, like these nonlinear programs, for example, we can efficiently find local minima. So we can still find these ones at very fast rates, but we don't know if they are global or local, right? So we have to be satisfied with these local minima. I think the difference in practice isn't so big, because if you take a nonlinear program solver, you apply it to a convex problem, you will find the global minimum, right? So that's beautiful. And the interesting thing that I think we should always keep in mind also when we look at the next methods, and here I quote Larry Biegler, who tries to bring down the point, the following point. In optimization, we shouldn't think of searching for a solution. Yeah? So it's not like searching in the darkness until we find a minimum. Yeah? In 10,000 dimensions, we will never find a minimum by just searching. Yeah? We solve an optimization problem. It's more like setting up an equation system and solving this equation system. That's what we need to do in optimization. It's not searching, but solving optimization problems, right? This is a little linguistic distinction, which I think is bringing home the point of, let's say, what we want to do here is we want to basically solve the optimality conditions, like setting the gradient to 0 and maybe solving this with a numerical method. It's not just trying out points. Yeah? That would be searching. Yeah? And searching is typically extremely slow, while solving can be extremely fast. That's actually what I should say, what I did in my internship at this bank, insurance company. So the Excel optimizer at that time was actually search. It was a search method called Nelda-Mead. It was just trying some points and somehow going loosely into directions that are somehow getting better. While then the QP solver just took this whole thing as a QP, knows that there's a little bit of linear algebra, do some reorganizations, tick, 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 and the solution is there, right? So this is solving an optimization problem. And convex ones you should definitely solve and not search for a solution. Yeah? For nonlinear ones, you can debate if there's some part, maybe some nasty problems you want to just try out, lots of samples, but mostly actually you also profit a lot from derivatives. And that's why also here derivative-based optimization plays a role. That will be in the next part of the talk. But before we do that, I want to stop the camera, stop the recording. And I want to comment on Newton type optimization algorithms. And there's one notion that will be throughout used, and I think it's useful to have this abbreviation available. So Newton type methods are always based on linearizations of nonlinear functions. So this concept of a linearization is absolutely crucial for everything that you do with Newton's methods and its variants. So if you have a function f, denoted here, the nonlinear one, and you have a point x bar, then the linearization of your function at that point is the first order Taylor series, which you can write down like this. So there's a constant term, and then there's a matrix, and that's multiplied with a vector of differences between x and x bar. Huh? So imagine this picture, and then you know what a linearization is. df by dx is a Jacobian matrix with lots of entries, potentially. And sometimes we denote these Jacobian metrics with a symbol that is misusing, I would say, the gradient symbol, right? It's if the function is scalar, it's exactly correct to use the gradient like we do it, namely like this. Here, look at the next slide. So here is the gradient symbol used. And if we have a function with several components, then the gradient symbol is basically nothing else than the transpose of the Jacobian. Yeah. So think of the gradient for any function, it's the transpose of the Jacobian, and then you're fine. So if you see this symbol, don't get confused, it's just a Jacobian. And the Taylor series FL of x at the linearization point x bar is, I think, a good shorthand for this clumsy part on the right, because that's summarizing what is the essence of it. So we have this first order Taylor series again and again. And some of the slides will look very messy until I clean them up with using this FL, right? So that's why I introduce it here. I will have 3 sections: equality constraint optimization, then inequality constraint optimization, and then how to solve QP subproblems. Because they are very important, I focus a bit on them. It's very high level and quick. And I try to jump through some of the math slides. They are, so to say, back up more. And I will stop longer at the simpler slides. So, but let's start. So we want to solve discretized optimal control problems, as we said, and they will turn out to be nonlinear programs, as we said before, big F, G, and H functions. So let's throw away the inequalities, because they will make things a bit more complicated. So just have equalities, which would be an unconstrained MPC problem with a nonlinear system model and a smooth objective function. Like many of reinforcement learning, we would have just no inequalities, right? Then we have this at the bottom, and let's look at what would be then the optimal solution. So since Lagrange, we introduced these Lagrange multipliers lambda, add up all the constraints to the objective and call this the Lagrangian function, which is depending on x and lambda. And then there's a little theorem that says that the optimal solution, if you have a local minimizer, then there exist multipliers such that this Lagrange function has a gradient that's 0. But of course, also the equalities should be 0 in order to make this point a feasible point. Yeah? So these 2 conditions, they're exactly as many conditions as we have variables. Yeah? X has as many variables as the gradient of lambda of L, right? And lambda has as many components as the second equation G. G has exactly as many components as lambda. So what we have here is what we call a square system of nonlinear equations, exactly as many unknowns as we have equations. So we can solve it. That's the solving, right? Even if it might be nonlinear, we can solve it. And that's what Newton's method does. And so if you have this nonlinear equation system, you linearize it. And here's the clumsy notation. Don't think of it. Yeah? I throw it away. And I directly go through some slides until I have the linearization here. That is now the simple slide. So you have your nonlinear program. You just linearize your two functions, f and g. That's it. And then some technical thing, you add some Hessian metrics, as we call it. And in this session, and that's actually an important but subtle detail. So here you take the second derivative of your Lagrangian function with respect to x. That's a complicated object. It's a Hessian matrix. And this one is what you have to solve. It's still an optimization problem. And that is equivalent to the Newton step of solving for these root finding problems. It's just a different way to frame it. And I use it this way because this is a QP. It's a quadratic optimization problems without inequalities. And QPs we can relatively easily solve. I should say they are actually solved like, now I go back actually some slides, but what you see here at the top is a linear equation system actually in the variable delta x. So actually a QP can be solved by a little linear solve. I will not detail that. But I directly jump into inequality constraint optimization. And inequality constraint optimization is only a little bit more complicated. So we add to the Lagrangian function also these multipliers for the inequalities that we call mu. And then one can state some conditions which go back to Karush and Kuhn and Tucker, three mathematicians that established them in the 50s and 60s. That if you have an optimal solution x star, then there exist multipliers lambda and mu that satisfy these conditions. The first one looks like the old Lagrange conditions, but then the last three, they are the so-called complementarity conditions, and they basically state that an inequality can be either active, the age can be 0, but then the mu must be, I mean, if the age is 0, then the mu can be non-zero, and otherwise, if the mu is if the mu is positive, the age must be 0. And if the age is positive, that means if you're in the interior, if your constraint isn't active, then the mu must be 0. Yeah? But I will not detail this. It's just a system of nonlinear equations, but this is non-smooth. And why is it non-smooth? Because of this complementarity condition here that basically makes that h and mu are on an L-shaped set. For each component of h. I will not detail that in much detail, but I just want to say that we can basically follow the path that we just did before, and I go to the simpler slide here. This is the simpler formulation. So you can actually do the same trick as before. You just say, I linearize my nonlinear functions. Add some iterate, xk. I add this extra Hessian term, which now should be the second derivative of this new Lagrangian. And if I solve that, I get a new iterate for all my three variables, x, lambda, and mu. So that would be a very nice iterative method. And that is actually really what is called sequential quadratic programming. Typically with inequalities, it gets interesting. But we didn't specify how to solve such a problem now. This isn't as easy as solving a linear system because we have the inequalities. So that's more like in the spirit of linear programming. And before I go into how to solve it, I want to go into something. Here's the simple slide again. The constraint Gauss-Newton method. And that's a method that's extremely useful and I think underused in the field of optimization, at least in practice. It's not so many people use it as should use it. Because very often we have these beautiful nonlinear least squares problems where we have lots of residuals. We call them R. R is now a vector valued function. We square them and we add them up. That's basically what trajectory following, state estimation, lots of problems fall into this class. So this objective function has a very special structure. And if you have that, then you can approximate this Hessian that we mentioned before by another matrix that is called the Gauss-Newton Hessian. And if you do the math, then after some reorganization, it looks extremely simple. And that's also how I recommend to remember this method. The QP subproblem that we just formulated previously, but with this Hessian, after massaging it a bit, you get just, it's like as simple as this. You linearize your nonlinear functions R, G, and L, H at some point, and you just keep everything that was convex, namely the squaring outside of the R, and the equality constraints and the inequality constraints, you get that. And that way you have a QP subproblem which is guaranteed to be convex. It's a semi-definite matrix, what we have here. And this problem you can then solve with a convex QP solver. And this is a very reliable, nice method called the constraint Gauss-Newton method, which I want to summarize here again. So you have a nonlinear least squares problem on the one side here, the left. You iterate like the following on the right. You have these subproblems at some linearization point xk. You linearize all functions, you solve a QP, and you get the solution as the next iterate. And that's where you linearize again, and then you repeat that whole thing. And you can show that this whole procedure has linear convergence. That means the distance to the true solution shrinks with a constant kappa. Kappa should be smaller than 1. We call it the contraction rate. And one can prove that this is small if the residual is small. That's a very interesting property, because the residual is exactly what we want to be small, right? So if you have a trajectory following problem where you can actually follow your trajectory quite well, so your deviation isn't too big, then your Gauss-Newton method will have a very good contraction rate and will work extremely well. If, on the other hand, you have a fitting problem, like a model fitting problem, you want to fit a model to data by nonlinear least squares. Also here, Gauss-Newton will converge fast if your model is able to fit your data well. So that's exactly when you have a nicely formulated fitting problem or a nicely formulated control problem that you can actually solve, so to say, then this method works fine. And it's as simple as this slide. So just remember the slide, and then you know, I think a method that can solve 90% of all practically arising nonlinear optimization problems. Very often least squares type. But we didn't specify how to solve the QP, so I need to still comment on that. So how do we solve a QP? So for equality constraint QP, I said it already, this is easy. You just solve one linear system. Here we have this linear system. You see it's x and lambda, they are the unknowns, and that's it. So I don't talk more. It's a backslash operator in MATLAB, so to say, or some structure exploiting linear algebra. But if you have inequalities, there exist two big families. I mean, there are more, but two that I want to mention here. One is the active set methods. And they are somehow similar to the simplex method for linear programming, which was the one that made the field of linear programming big, right? That Danzig's simplex method, basically. That's not explained here, but that's yeah, basically a very interesting class of algorithms. And then there's the other field that became popular about 15 years ago, 20 even, interior point methods. And they are explained a bit here because they are also very competitive and nowadays often used for lots of optimization problems. So on 2 slides, interior point methods, very fast. So let's regard an inequality constraint QP in a kind of modified standard form. So you see here that all the x variables are positive, and that's my only inequalities. I can always add some extra variables to make every problem into this form, I should say, right? There's always some tricks with so-called slack variables. So let's just accept this is the form in which we have our QP now. And then the idea is these inequalities, that x should be positive, you can replace it by a so-called barrier function that says if the x is coming close to 0, it gets incredibly high cost by penalizing it. And we take this minus tau times the logarithm of x. So the logarithm of x gets minus infinity if x comes close to 0, right? And then with a minus sign, it gets plus infinity. So this is a barrier that will not allow you to ever touch the constraint 0, right? So you will be pushed away into the interior. And so now you have this convex barrier subproblem in the interior point method, which we see here in the middle, which just takes the original QP objective. It keeps the equality constraints because we said these are easy, but then it adds this convex penalty here. It's not a penalty, we call it a barrier, sorry. This convex barrier function here, and that will ensure that we will always stay in the feasible set and inside actually the feasible set. But now the real working of an interior point method is the following. So you have for each tau a different problem, and if you make tau very, very small, your barrier problem is basically as if there would be infinite penalty for 0 and below 0 and no penalty for positive x, right? So it's actually approximating the original problem very well if tau is very small, but it's also getting this complete non-smoothness back into the picture. So you typically there's algorithms, they start with a big tau, very big tau actually. They solve this problem. This is nonlinear, right? But what is it? It's convex, right? So for a fixed tau, this is a convex problem. You can reliably solve it, find the optimizer, and then, and that's just a few Newton steps. And then you take this optimizer, you reduce tau, and you solve the new problem for the smaller tau with the old solution as initial guess. So Newton's method very much depends on a good initial guess, right? These linearization points, and you slowly reduce tau. And then while you reduce tau, you follow your solutions and you get to a really highly accurate solution when tau is approaching 0. And one can show that if you reduce it by a constant factor every time, like reduce it by 10% every time or something, that would be a slow step, a slow method, then each new problem would only take a bounded number of Newton iterations. So the alarm clock tells me that we should stop in a few minutes, which we will do. And one can show actually that this has polynomial complexity overall to get an epsilon suboptimal solution, and epsilon can be extremely small. So this was a big, let's say, surprise sometime in the 90s, where people got very excited because these were the first methods for linear programming and quadratic programming that had actually a polynomial runtime guarantee, which the simplex method doesn't have, by the way. So basically confirming the fact that convex optimization is easy. So these nonlinear systems in the interior point methods, you can, after some reformulation, you can show that they are just the Newton system, I mean the optimality conditions for that problem. They are this nonlinear system that we see here at the bottom. And here you see the only nonlinearity is the product of x times mu. And that one is really easy to linearize, so to say, and you can apply Newton's method to that root finding problem that we have here. Please note, this has also exactly as many unknowns as it has equations, and it's just smooth now because the tau is positive. And then you can solve it with this interior point method, and that's a route that's taken in many QP solvers. And one I want to mention is the solver HPIPM for fast MPC, which also, in addition, exploits the structure of optimal control problems and is able to solve, optimization problems in microseconds, QPs in a few microseconds. And I should say, and that's also important for the exercise in this course, is that this whole idea of interior point methods, which is more theoretically founded for convex problems like QP here, but you can also apply it directly to nonlinear programs. Yeah? So you could also say, hey, let's not think about these SQP and so on, but directly say, add the barrier to your nonlinear function and then apply Newton's method from the beginning and do the path for the nonlinear problem. And then you enter the domain of nonlinear interior point methods, and that's what is, for example, implemented in the solver IPOpt, which is a very useful and powerful solver, open source solver for nonlinear programming problems that we will also use in some of our exercises. IPOpt was actually written by Wächter and Bigler. Bigler, the one who stresses that we should solve optimization problems rather than search for the solution, right? So IPOpt also solves nonlinear programming problems by different derivatives and solving basically linear systems in each step. So let's summarize all this. We already mentioned what optimization problems can be. I will not repeat that, but please keep in mind some important classes. I think never forget linear programs, right? Never forget quadratic programs, and never forget nonlinear programs. And Newton type optimization is typically a method for nonlinear programs, and they just work by linearizing nonlinear functions. That's very easy to remember, right? And if you want to keep something for the next lectures, look at the right, and that is that general NLP would be stated like this with big F, G, and H, right? So that's what we want to solve all the time in also in optimal control. And in this very special case, which is sounds a bit special, but which is actually extremely common in practice, of nonlinear least squares, where your function f is actually the sum of squared residuals. In this case, please remember this Gauss-Newton QP subproblem. Just linearize your problem, all nonlinear functions, but under the square. And then you get a QP, you can reliably solve that, and that brings you already very closely to solutions of complex, large-scale, nonlinear optimization problems in one iteration, typically. And after 5, 10 iterations, very often you have solved them. So this is something to keep in mind. Gauss-Newton, actually, we should be correct. It's the constrained Gauss-Newton method, because Gauss-Newton with constraints, right? That's the method that I recommend for lots of problems in practice. And you can generalize that to other techniques we call sequential convex programming, but I didn't want to go into the details here with you. Just give you the most useful, and that is the Gauss-Newton method. So don't forget the Gauss-Newton method. Okay, that's one of the things I want to share with you. And if you want to read more, there are excellent textbooks in the field of optimization, in particular this first one by Nosedal and Wright, I like a lot. There are older ones, also this Lüneberger book on nonlinear programming. These are good and interesting optimization books. And I should say, if you want to learn more about convex optimization, the standard book here is the Boyd and Van den Berge book. It's very nicely written, has lots of exercises, and you can download the PDF, which is also useful. Yes, that's what I wanted to say about numerical optimization. What I could say in 1 hour was tough, fast, but I hope you got the flavor of this field. And I thank you very much for your attention. Thank you. So we have stopped the recording.